0.4. 0.433.
Yeah.
Are you sure?
Yeah.
Positive?
Positive.
Yeah? Okay. I'm gonna believe here, Mr. Like Tyrell from Game of Thrones.
Yes, exactly.
Aren't you guys looking forward to the final?
Yeah.
Yes. Yeah, me too. Waited 2 years. Oh, okay. So there you go. Now you have what is the what is the gradient for hydrostatic pore pressure? Okay, probably you already knew that, but now we need to get into something a little bit more complex, which is calculating vertical total stress. So this is how you calculate pore pressure, right? You know that very well. You multiply that number times depth, and you will get here this pore pressure. Okay, so let's continue over here. Let's say that now we go to the field somewhere in West Texas, where, of course, you know, you're gonna find Longhorn somewhere over there. And you also want to drill a well at a given depth Z, at that point over there. You also know that that point, that piece of rock in a reservoir at a given depth, as we said before, it's well communicated to the surface. So there is a continuous connected pore space that communicates pore pressure. Question number 1, what is going to be the value of pore pressure as a function of depth? This is what we just saw, right? So pore pressure is going to be equal to the density of the water, if we assume the density of water constant, times G times Z. All right, so here is where the new thing comes. We want to calculate what is the stress acting on that piece of rock. All of geomechanics related to rock deformation and rock failure or breaking rocks, and that depends on the stresses. So in addition to the pore pressure, we need to know the stress. This stress, we're going to call it SV, and for now it has a long name, but we're going to start the meaning of all of these words in detail later on. It's called total vertical stress. Some other times also goes simply by overburden. So we want to calculate that value. If I want to calculate all of the weight on top of this, what do you think we should do? If we find similarity with the previous equation.
Average density of the rock.
The average density of the rock, and so what? So this is going to be, let's say, this SV. I'm going to write the equation, and it's going to look similar to this one, right? But instead of the density of the water, the only thing I have to do is to write bulk density of the rock, and then it's going to be the same, times G times Z. What is the bulk density of the rock? If, let's say, I have a rock with pores that are filled with fluids, the bulk density is going to be what is called a volume average of the densities of all what is inside. And that's going to be equal to the density of the rock matrix times, what do you think? Let's use some variables that
Or 1 minus porosity.
1 minus porosity, very well, plus what? Now the weight of the fluids.
Porosity fluid times
Density of the fluids
porosity.
times porosity, right? This is what is called the volume average, because it's the average of the part of the matrix times the part of the fluids. In homework number 1, you're going to be calculating this, but with one more level of detail. Rocks, many times, they are composed by several types of minerals, right? So this, the density of the matrix is going to be equal to the concentration of mineral 1 times the density of mineral 1 plus the concentration of mineral 2 times the density of mineral 2 plus as many minerals as you have in your rock, and with the corresponding concentrations, right? Where the summation of all of these concentrations is equal to 1. And what about the fluids? Fluids is going to be very similar, right? The density, average density of the fluid is going to be equal to the density of the water times, this one you know. What should I multiply this one for? Saturation of water plus the density of the oil times saturation of the oil plus the density of gas times saturation of gas, where, same as before, saturation of water plus saturation of oil plus saturation of gas equal to 0. But equal to 1. Thank you. So, do you think that the density, the bulk density of the rock is going to be bigger or smaller than the density of water? How much times bigger? A lot. How much is a lot? 3. You say 3. I would say not too close. I mean, in the right direction, but 2 times. I don't think we're going to have time, so I'm going to give this exercise to you to do it later. But let's imagine that you have a porosity of 20%, that you have a sandstone with a density of quartz. Yes, of quartz equal to 2,650 kilograms per meter cubed. And then you have density of brine of, let's say, it's a brine with not a lot of salt, of 1,000 kilograms per meter cubed. You put all of these into that equation, and you will get the bulk density is about 2,320 kilograms per meter cubed. So the answer is that the density of rock is about 2 times to 2.5, sometimes it's very heavy rock, 2.6 times the weight of water. And if I were to plot what that vertical stress here is, in this plot over here, it's going to be something like this. This is going to be SB. Again, this is going to be the total vertical stress. If you wanted to get down here and use a jack to lift the rock up, this is how much pressure in the jack you need. Basically, you know, this is the amount of stress or pressure you need to lift the ground up. And sometimes we do that with hydraulic fractures. So don't think that that's a crazy idea. Okay, so let's see now one more very important concept that we're going to see through our geomechanics. We have the total vertical stress, which is the total weight of the formations on top of a given location, and we have the pore pressure. The difference between those two is something very important, which is called effective stress, and we're going to denote it by sigma. It's going to be sigma b, and in this case, this is going to be the effective vertical stress. Probably the concept is not super clear right now, but it's going to be clear when we talk about offshore. So this case is onshore, okay? I have 1 minute to go offshore. So let's go offshore and just illustrate the concept very quickly. You go offshore and you're interested in computing wellbore stability at a given location somewhere over here below the seafloor. Okay? Let's say that there is a well-connected path from the seafloor to that location. What is going to be pore pressure? How does pore pressure increase in the water? Linearly, right? So the fish is gonna feel that, and the pore pressure is going to increase linearly. Just 1 more minute, guys, so you're done. What about stress? Did you guys do scuba diving? Or probably when you go to the beach, if you dive to the bottom, can you pick up the sand in there, or it's like locked that you cannot take it out from the ground, from the sea, from the sea floor, or from the riverbed? You can easily just grab it, right? So there is actually no stress at that location. You can just move the sand apart because there is nothing holding it. And that thing which is holding it, that is what is called effective stress. So we're going to see on Monday that effective stress at the seafloor here is 0, and that the vertical stress, total vertical stress, is going to start growing somewhere, well, exactly at that point, and more or less like this, and our effective stress offshore now is going to be this one, starting 0 at the seafloor and increasing with that. All right? Okay, guys, so work on your homework, and I'll see you Monday. Have a good weekend.